All right. All right, everyone. So I'm Shirley, and I'm first year PhD student at Stanford University, and excited to be here. And thanks for the invitation. So today I'm gonna talk about a work called Discovering Invariant Rationale for Graph Neural Network, which is published in iClear 22. So yeah. So as you already see in the title, that our motivation is towards the interoperability of graph neural network. So the pain point of previous deep learning models like graph neural network is that they generally fail to exhibit interpretations about why the model makes certain predictions. So imagine we train graph neural network to predict the property of a certain drug. And maybe the predictor will just say, I have 99 confidence that this molecule is toxic. And as scientists or engineer, we can just, accept this result. So which is quite bad because there's no other information given along with the prediction. So it would be really helpful if the neural network can say, identify some important feature. For example, this graph here, which we call as rationale. You can, think of it like an explanation. So this subgraph is important for this molecule being toxic, and so that we could have some extra information about why this model makes prediction, so that we can draw insight from such explanation. And maybe for some reason, this scientists want to design more, toxic molecules in good purpose. I wish then he could just use such insight to design more drugs with it. And another motivation is towards the auto distribution generalization of deep learning models. So we can see that graph neural networks, they easily fail to generalize to auto distribution data sets. And by auto distribution data set, it is a data set that with the different distribution as the training data set. So here's an example about the graph classification task. So this task is constructed. Each graph is constructed by two parts. The first part is the base graph, which is highlighted in green, blue, and the yellow. So this base graph has nothing to do with the graph label. And then we attach a motif to the base graph as highlighted in red. And these are all house graphs. So the graph label will be determined by the type of the motif here. So we have three kinds of base graph and three kinds of motifs. So imagine we have a training data set where there's some correlation between the base graph and the motif. So that means 9 out of 10 house motifs are attached with the base graph. So in that case, if we train a graph neural network on it, and the network could easily associate the base graph with the house motif, and this could be very bad because the base graph is not the it's not an important feature to determine the label of the graph. So if we test this graph neural network in a testing data set with a different distribution than the training data set, so for example, the base has the equal probability to attach to the house motif, and this model could easily fail. So this is the same case if we consider different graph size or different node degrees. Such behavior, such property that the deep learning models fail to generalize to other distribution data set is quite dangerous when it comes to some real world data sets. So it's like some molecule data set where the train and the testing, that a subset are drawn from different domains. So our work here is try to solve these two disadvantages of previous deep learning models, specifically for graph neural network. So to be more specific, we assume such a data generation process. So this will be our assumption in this paper. So we denote G as a variable as the full graph. And we assume the G can be split into two parts. The first part is the shortcut and the non-causal part. It's like the base graph we described before. And the second part is C, means the causal graph. So the causal graph is the only feature that could determine the label. And moreover, it has a stable relation with the label along all the different distributions. So another example to validate this assumption is that you can think of some, as I mentioned before, some molecules where G will be the molecule graph and the S could be some, carbon structure, which, is not the core factor to determine the property of a molecule. And the C will be some functional group. Or if you think about some like sentimental classification task in graphs, so it's like each sentence will be a graph. And so the nodes in the graph are the tokens, and the edges represent the relation between the different tokens. So in that case, if we try to classify the sentiment for this graph, and the S could be some, punctuations or prepositions which don't really have sentimental meaning, and a C could be some positive or negative words like I'm happy or depressed. So it would determine the sentiment of this graph. So this will be our assumption in this paper, and we found that through this assumption, there's a clear solution to solve both of these problems. That is to find the causal feature C. In that case, we could, by identifying some important feature as the causal feature, we can iterate the interpretations to shed light into how the model make predictions. And the second is that if we can make the model pay more attention to the relation between the C and Y, because the relation between C and Y is stable in other distributions, so the model will less easily to fail in other like testing data sets. So how could we do that? And the core of this work is towards finding the causal feature C here. And yes, this will be a tricky problem. So why don't we step backward and see what are these conditions to the causal feature C and the S satisfy? So here's the invariant condition of causal and the shortcut features. And let's assume we already know what are these shortcut and causal features. And also feel free to interrupt me like during the process. And so.
Sorry, I have a really quick question. I just want to make sure I understand. Would you mind going back one slide? I guess I didn't fully understand. So I just want to make sure that I understood what you were saying. So you basically have this graph that has these two kind of structures, and one of them is very relevant and one of them is not particularly relevant, but appears very often. And so what you're saying is that what happens is because it appears so often, the graph neural network assumes that it's relevant and it kind of like drowns out the noise of the actually relevant one.
Yes. Yeah.
Okay, and then in this case, in the image, like the irrelevant one is the green one and the actually truly relevant one is the red one. And so basically you identify that as like important. And so you say that's the causal feature and it's stable because whenever it appears, it's, it means something. And that's kind of how you intervene.
Yeah.
Okay, cool. Just making sure I understood. Sorry, please go ahead.
No, it's a very good, cool. Yeah, so so the core of this our work is to find the causal feature, and now we like to see what are these conditions to the causal feature and the shortcut feature satisfy. So imagine we have hopefully you can see my mouse. So let's see so we have an original distribution which is the training data set, and assume we already know what the C and the S are, and moreover we can manipulate them. That means I can fix some value to the S value for S variable. So for example, I can fix an empty set to the S variable, which will give us this distribution with only the motive, because I remove the base graph. And I could also intervene this original distribution with some other kinds of base graph like tree base or the ladder base, which will give us like multiple distribution here. So here's a very like simple observation about what about the property that the causal features will satisfy. So the property is that no matter what value we use to intervene the S variable, as long as the causal variable is observed, and the causal variable is the motive graph here, so the graph label will remain unchanged. That means that the graph in the first three columns will still be labeled as house because we don't like intervene on the causal feature. and the fourth row will still be labeled as circle. So for convenience, we call this different environment as the S intervention environments, and the S is determined by the value we use to intervene the S variable. So this is the condition that the causal feature should satisfy, and but in the real world, we only observe the the full input and the label Y. So neither causal feature C or the shortcut feature S is available to us. Then how do we do this? So to formally describe it, we first formulate any intrinsic interpretable model as this form, which is basically two parts. The first part is that we try to discover a rational C-tilt from the observed graph. So this is the first part of the model. And the second part is that we based on this exhibited rational, and we try to try to output the prediction to approach the true labels here. So based on this formulation, we sort of change our targets here as approaching the causal feature C using the rational C-tilt. And so after we write this equation, we could find some clue about why previous methods. So they also fail to generalize to other distribution, and by previous method, you can think of some method in the graph, like a graph attention model or some pooling methods. They also try to find some important feature, like using larger attention values, but they also fail to generalize other distribution. And the reason is that they only try to minimize the empirical risk between the model prediction and the label, based on the assumption that the rational is informative for predicting Y. But we found that they missed a condition, that is the invariant condition we mentioned before. That is, we hope the label Y and the shortcut feature should be independent given the observation of C-tilt, which means that the changes on S will not affect Y as long as C is observed. So what's following is that we try to put this constraint into our optimization process and make the causal feature we found satisfy to the the invariant condition. And so that's why we propose the DIR principle and the corresponding objectives. So our principle has two terms. The first one is that we try to minimize all S intervention risks, and the second one is that we want to minimize variance of different S intervention risks. So here's some example based on the previous slides, and so assume we have multiple distributions here, and we can compute their risk under different distributions. So you can think about cross entropy loss for individual distributions. So for example, the loss will be some values like 0.5, 0.3 here. So the first one means that we try to minimize the risk under each environment. And the second one is that we hope that the risk across these two, 4 distributions will be as uniform as possible. So again, the first one is that we try to make the rational be informative for predicting Y, and the second is that we try to exhibit the invariant condition that we mentioned before. That is, we hope the S and the Y will be independent given the causal feature C. And specifically, we use the variance to punish as the penalty to punish the difference between the risk difference of the risk between these distributions. Okay, yeah. So the remaining question will be, how could this objective help us find the causal feature? So that is why we also bring some theoretical guarantees. And yeah, so there's basically two theorems here, and the first one is the necessity condition. That means that if we have a oracle model, say it's the ground truth mapping that could predict the label Y, and this ground truth model will satisfy to the DI principle here. And the sufficiency condition means that under certain condition, we can approach the causal feature or say the like Oracle model by training a model satisfied to the DIR principle. Yeah, so this is basically the our core formulation here. And yeah, I can take questions, see people if have questions. I can, stop a little bit. Yeah, cool. Yeah, then I can go on and I can take questions afterwards. All right. Yeah, so when it comes to modeling, we have 4 parts basically. So we have a rational generator. So this generator basically try to split the graph into 2 parts by generate some salt mask on the graph. And then the distribution in the Venner is and to like create some interventional distribution, as I mentioned in the previous slide. And the third part is the shared graph encoder, which will encode the S and the C graph individually. And we also have 2 classifiers to output the prediction given only the shortcut feature and the causal feature. And then we could get a joint prediction at the end and try to optimize the DIR principle and the objective. So here's a demonstration. So assume we have a batch of the input graph here. The rational generator will try to split the graph into 2 parts. One is the rational part, and the other is you can think of as a non-causal or redundant feature. So basically, the way we construct the rational generator is that we produce the mask on the graph. So for example, if the edge on the basically is we try to produce the edge weight on the graph. So for example, if the edge weight is 0.1 in the C tilt, then the corresponding weight in the S graph will be 0.1 minus 0.1, that is 0.9. So after that, we will have a distribution in the Venner, which will sample like subgraph from the S pool here, and fix it at the end of this rational generator. So next, the shared encoder will like encode this subgraph and this batch of subgraphs individually, which will produce the predictions given only the shortcut feature and the causal feature, and then we like construct the S interventional distribution in the representation space. So there's actually some details in the modeling, but this is basically the core idea in our work. That is, we use the intervenor, that is, try to use the existing data in the data set as the candidates to do the intervention and create multiple interventional distributions. So based on different intervened subgraphs, it's like we can sample multiple, like subgraphs from the S pool. So correspondingly, we will have multiple S interventional distribution here, which will enable us to compute the DIR objective. Yeah, so there are some details like at the end of this part, and yeah, maybe I can also talk a little bit. So as you can see that one difficulty of the graph data is that it's hard to combine them in the feature space. So if you think about this subgraph and this different subgraph, and we try to like merge, attach them, there's actually multiple ways to do it. And the fact is that we also use the salt mask on the graph. So this will make it hard to really do the intervention in the feature space. So instead, we try to merge them in the representation space. So that's why we encode them like individually, and then get a joint prediction based on their individual softmax output, and then we should get the S interventional distribution. So this might be a bit different from what previous slide demonstrates. And we also include the like shortcut branch to optimize the prediction given only the shortcut feature. So basically, we optimize the cost entropy loss between the output between the prediction given the S graph and the true level. So we also need to like detach the optimization of this branch from the main part, so that we could prevent the learning of the shortcut feature to the main parts of our model. That is, we try to remove the bias here. Yeah, so but you know, these are some details, and yeah, I will help people focus on the construction of S-interventional distribution here. And yeah, so this is basically our modeling. And yeah.
Sorry, I have a quick question. You were saying that there was that it's difficult to like kind of like merge the graphs together. I didn't fully understand like where that complexity comes from, because if I understand correctly, you have this input graph, then you train something to separate it, and then you have a bunch of options, and then you kind of permute them together to create your like S intervention distribution. And I guess I didn't really understand like why that would be difficult.
Yeah. So one difficulty is that there's multiple ways to do it. So if we just have a like discrete subgraph here, like we can you know, attach these two subgraphs. Basically, we need to find different nodes to do it. Like, you know, the nodes that we could attach like different subgraphs. So this is the first. And if you so the second is that, so basically we so what this rational generator produce is the salt mapped on the graph here. So it's not a discrete graph. And yeah, one, you know, confusion is that I didn't draw the subgraph here because it's like something we rule out, but there's some edge weights on the this part of the graph. So this is actually two full graph here with different edge weights. So this is not, you know, discrete subgraph that we could easily join them. Yeah, so I guess these are the two reasons that
Okay, makes sense.
Why it's hard to do it. Yeah.
But can I ask like why you decided to make it? So let's say you have these edge. Maybe I can save this question for the end, actually. Why don't you keep going? And then I'll ask more later.
Yeah, sure. Cool. Yeah, so there's few some experiment results, and the first one we are interested in what are these rationals and how good are they to correspond to the ground truth explanations. So here we compute the precision on the spurious motive dataset. That is the base graph and the, you know, house motive dataset I described before. So besides, we also introduce the variable B here to control the bias in the training dataset. So balance means that each base graph has the same probability being attached to the house motive, and if B is large, means that the correlation between the tree base and the house will increase. So we compare the baseline, including some, you know, gravitation model and some pooling methods. So basically, we seen the attention value or the pooled subgraph as the result of these rationals, so that we could, you know, compute so that we can rank the edges based on their edge weight, and then we can compute their alignment between the ground truth motive here. So as you can see that the precision of the rationals in DIR like outperforms all the baseline models like to a large extent, and these are some visualizations of the rationals we found, and you can see there are still some noise, like it also found some like other edges in the base graph, but basically it could still look for the links in the motive. That is one good thing for it to you know, discover some like correct rationale based on this full graph. And we also use another like visualization on the graph SST data, which is probably more interesting than one. So this is sentimental classification data set. So each graph will represent a sentence, and the node will be the tokens, and the link will be the relations between these tokens. So for example, this graph means a majestic achievement and epic of astonishing grandeur. So this graph will have positive sentiment, and the first row is the training rationales we found from the training data set. So we can see that the rationales can represent some including some positive and negative word, including majestic and worst. And when it comes to the testing data set, so we create the distribution shift between the training and the testing data set by making the graph in the testing data set smaller, which also have smaller node degree. And we found that our model could still find the sentiment like surprising or like middling associated with the sentiment. So this will give us two conclusions here. And the first one is that the rationale could emphasize the token that directly result in the sentiment, in the sentence positive or negative sentiment, and also occurs persistently on the causal features for outer distribution testing data. And this is also one of the factors that contribute to its like task performance in outer distribution data sets. So besides the spheres motif data set, I mentioned before, we also use the minutes superpixel data set and the graph SST2 data set and also a molecule data set motif. So we besides the interpretability baselines, we also compare our method with several invariant and robust learning methods. So basically, they also try to find a good representation space that without to rule out this bias. And this is the ablation models. That is basically we the aversion after removing the variance term. That is yeah, I can go back a little. Oops. Yeah, so this ablation model is basically set the lambda to 0, which will leave us only the interventional expected interventional risk here. All right. Yeah, so we can see that DR still outperforms the baselines, and also another interesting observation is that we found these interpretability methods, they sort of underperform the empirical risk minimization when the bias is large. And as for the invariance or robustness baselines, they like underperform ERM when the bias is small. So this you can see like there's a trade-off between different methods, and then they are specifically developed for the data sets with different bias. But this is just not practical. Sorry, just not practical in the real world, because we don't know like what extent are the bias in the model. So we can see that DIR can like consistently outperform them, and across different extent of this bias. And as for this data set, the distribution shift we created is that we try to inject some noise to the null features in the testing graph, so that there will be a gap between the distribution of the null features. And the motif is a benchmark in the GB data set. So this result will demonstrate the power of using DIR to generate to our distribution data sets. And we very interesting, we also like discover a two-step training dynamics, which we code as the adaptation and fitting dynamics. So the thing is that we found that so here we visualize the value of the DR penalty, that is the variance term, with regard to the training process, and also the precision value we compute before, like during the training process. And we've found that the variance penalty is first increased, and then it gradually decreased to a low value, almost 0. So as the penalty could like reflect the extent the model break the DIR principle. So we attribute such such a thing as that the learning of the at CTOs, that is we try to that is the learning of the rational generator. It's mainly conducted during the initial training process, and it's basically try to explore the rationals that satisfy to the DIR principle at the early stage of the training process. To validate it, we also visualize the rationals based on their embeddings. So we visualize the rationals at different stage of the training process, and we can find that there's a large gap between the stage 1 and 2. That means that the rational change like dramatically between the stage 1 and 2. And the second stage is fitting. That means that they are mainly optimized the second part of the modeling. That is the H Y hat to consolidate the functional relation between the C tilde and the prediction Y until the model converges. Because the evidence is that the rational embedding between stage 2 and the 3, it only makes small changes, and we can find that at the second stage of the training process, there is no much there's only slow improvement on the precision, and yeah, so this demonstrate the adaptation and the fitting dynamics in the DIR principle, which is quite interesting to me, as it's also like it's sort of like aligned with our expectations that we should firstly look some features, important features that align with the DIR principle, and then the second stage is that the model will try to predict the label from this exhibited rationals. So yeah, so after we observe a strong correlation between the variance penalty and the precision metrics, we also found a similar conclusion for the IRM method, which is the invariant risk minimization. And yeah, for people who are not familiar with this method basically try to find the trying to train an encoder so that the classifier on top of the encoder could be optimal in different environments. Which so they also use the gradient penalty term to do that. And yeah, we can find that the variance term of this IRM method, it also follows a similar pattern to the DIR penalty, which is that the penalty first increase and then decrease. But while the IRM method, it consistently outperforms DIR with regard to the training accuracy, as you can see in the graph in the figure here, its testing performance decrease in the testing data set. And we one potential explanation of that is that the model will gradually overfit at the end of the training. That will make the model learn from the various correlation from the data set. And yeah, so the overfitting issue is serious issue in the real world training, and which is also something we need to avoid. And here's a small personal note here. And so in the implementation of DIR, we sort of use the early stopping, and I found that the early stopping is actually very important for the DIR to perform well. And the intuition is that we try to find the representation of the rational generator and as well as the shared graph encoder to find the good predicted power between the causal feature C and the label Y, while we don't want the model to learn from some other spurious correlations. That is the first thing. And the second thing is that we try to find a good rationale that satisfies to the DIR principle. But if you think about this process, the for over parameterized neural network, it will gradually it will overfit at the end due to the property that we have much more parameters while we only have a small subset of the, training data set to train. So that means that the model will gradually learn from some potential bias at the end. And we try to catch a good model in the middle of the training process. And that is why the early stopping is an important part in the implementation. That is to guarantee both the generalization power of the DIR as well as we can find good rationales here. Okay, yeah. I think I can take some questions before I wrap up on this methodology and talk about some future work. So, but I guess the core idea of this work is that we try to find the causal features, and we do it by constructing multiple interventional distributions here, and we multiply the effective risk as well as the variance of the risk along across the different environments. So the construction of this interventional distribution is actually a bit similar to the idea of data augmentation. It's just that we try to conduct it in the representation space to guarantee the feasibility of the implementation. And yeah, so.
Yeah, I have a question. Would you mind going back one slide?
Oh, one slide.
Yeah, I guess I'm having trouble interpreting the t-SNE visualizations, like and tying them to what you were talking about with like the adaptation. So if I understood correctly, when you said the penalty, this is for the variance.
Yes.
For the variance. So then I guess in the first step, the goal is to basically distinguish like these like two categories, the ones that are like very useful and the ones that are like really not useful. And then in the second one, I guess I don't really understand like the difference between like 2 and 3. To me, it looks like there's 2 stages, but it seems like you're indicating that there's 3. So I was wondering if you could explain that.
Yeah, sure. So the first stage is that the model will try to find good rationals, and we interpreted this conclusion by compare the stage 1, the visualization in the rational embedding, and the stage 2. So we can see there's a dramatic change between these 2 stages. And so we interpret such thing as that the model will first try to optimize try to find good rationals. So that is why the embeddings change to a large extent. And the second stage is that we can see that there's no much difference between stage 2 and 3. So which indicates that you can think of the graph. Sorry, I should put this in the. Okay, yeah, you can think about this graph. That means that because the rational is fixed in the middle, so this could only indicate that the model will try to optimize the second part of this modeling, which is that it tries to find the relation between the rational and the label y.
Okay, yeah, that makes sense.
Yeah, so that is why we code as fitting, and this process will conduct after the rational is well exhibited, and then until the model converge.
And then I guess what you were saying, if you could go back to the slide we were just at, sure. I think. I am not personally as familiar with IRM. Would you mind explaining the next slide? Yeah, a little bit further. So you said that it's like there's an encoder and then there's a classifier on top of the encoder.
Yeah, so you can think of encoder that is try to get a high dimensional embedding from a graph, and the classifier is the last part of the model that is try to use the embedding to get a prediction. So you can think of it as a linear layer or NLP. So the core idea of IRM is that it tries to find a representation that is the embedding of the data, so that if you have like multiple environments and you can fine tune like different classifier in different like environments. So if you find the correct representation, then the classifier should be optimal in each individual environment. So they sort of make this optimization problem more feasible by using a gradient penalty term That is to they sort of introduce like dummy variable in their objective function, and but I guess the idea is similar to our work here. That is, we also, but we solve this problem from the perspective of the rational, and we also use a different different mechanism to construct the interventional distribution. So one problem with the IRM besides its method is that it sort of assumes there's some already prepared environments. So like if you can think of it as it sort of assumes that the graph distribution already known to people, that is, for example, the distribution we conduct here, like we sort of use the intervention to construct different environments. But the assumption of IRM is that they already know the environment. So you can think of each environment as the motif attached to different base graphs. But this is, we sort of assume we don't know this knowledge, and then we try to do it by ourselves, by the intervention. Yeah.
So if I understood correctly, like your method is kind of introducing the idea of like robustness by a kind of, like you were saying, like data augmentation, versus like theirs, they just like take the graph, encode it, and classify, versus in your case, you're first perturbing the graph to some extent and then encoding whatever and classifying.
Yes.
To some extent. Yeah. Okay, cool. I understand.
Yeah, also so the encoder and the classifier is also different from our concept here. That is, we try to use the like generator to generate the rationals. So that's also one another difference.
Okay, that makes sense. Those were all my questions. I don't know if anyone else has questions.
Yeah, these are good questions. Yeah.
I guess not. Keep going. Go for it.
Cool. Yeah. Nice. Yeah. So I will wrap up by talking about some future directions. And yeah, I was like enjoy this part, as I always think like future directions should be like more important, maybe more important than the work itself. So I guess some extensions, based on our work, is that we need to like improve the expressiveness of the rational generators, because we assume the rational generator could capture the different kinds of graph structure. Like basically, you need to identify like a varying graph, different graphs in the data set, and also capture the difference between the node features. And the second one is that so we sort of create a pool containing all the like potential spurious shortcut features, and we sample one like subgraph from the pool to conduct the intervention. But the problem with it is that we sort of use the existing spurious patterns in the data set. So when it comes to unseen spurious patterns, it will be hard, could be harmful for our method to generalize. And the third future direction is that maybe we need like some more general assumptions, because our assumption paper is that we assume the graph can be split into two parts in the feature space. And particularly one part of them is the reason that why this graph is have certain property or have the certain level. So this assumption sometimes will not hold true in the real world. And if you can like think of more like complicated like social graph, this assumption we will need some more general assumptions to deal with this problem. And the last is that also one interesting direction is that we can think of some higher level interpretability. So this is also associated with the third one, that is sometimes the graph can be split in the feature space, but it's possible that we can identify the interpretations from their representation space. So that is to say, so if I have a graph here and I could encode it, using the encoder, which will give us the high dimensional embedding here. And it would be interesting for us if we can like identify some dimensions in this embedding that is associated with specific subgraph in the feature, and also like we can split them, like distinguish them, and particularly one several dimensions in this embedding could have strong association with the graph label, and particularly is the causal dimension. While the others could be some like redundant or non-causal dimension, and which is also another kind of interpretations that could shed light into how this model make the prediction. And the second one is that we could also distill in some abstract variables. So if you think about some image neural network that try to identify try to do the face recognition. So sometimes they will use like this entangled representation learning to learn some abstract variables, like to control the size of the eye or the smile. So it will be also possible if in the graph we can identify some abstract variables that control some global patterns of the graph, like some clustering efficiency and then maybe the graph size, and also some variables that control the local patterns, like different like connectivity or degrees. So these are all like which I think are some interesting directions that could explore in the future, and also could go beyond the limits of this work. Okay, yeah. So yeah, thanks. And this work is done during my internship at Stanford in the Net++ lab, and these are the link of the paper GitHub, and also some contact information. Yeah, feel free to ask questions if you need. Yeah.